Move on now to our dynamic spirometry measurements here. And in the lab manual, you have an overview of obstructive and restrictive disorders here. The page that is not numbered, which is page 60, has two diagrams on it. And we're going to come back to this, this page in just a minute to make the measurements that will give us our indication of obstructive disorders, and also give us some indication potentially of restrictive disorders as well. I'll discuss that with you. Let's go back to this tutorial. And so we finished this section here. Now, the second part of this tutorial covers the dynamic spirometry measurements. And the specific dynamic spirometry measurement that, that we're calculating here is discussed on the next slide. That's called the FEV1 to FVC ratio. So let's just once again run through the dynamic spirometry setup here. We want to keep in mind that the main difference here between the static and the dynamic spirometry for purposes of the lab exam is the element of time. The dynamic lung test take into account the time it takes you to exhale, and if it's a machine that can measure inhalations, the time it takes you to inhale as well. And for our purposes, we're not only interested in the total time it takes for exhalation, but how quickly you can exhale, right, in order to get an indication of obstructive disorders. This video here, you can't really see on this PDF that this is a video, but there's an embedded video here. There's a link to that video on YouTube. This is the video that shows the dynamic spirometer that can allow for inhalation measurements and exhalation measurements in terms of volumes. So as the individuals breathe in and out, you'll see the drum go up and down, and you see the pen on the paper go up and down. Down indicating expiration, up indicating inspiration. Right. The type of measurement we're interested in here is the forced vital capacity measurement. And so this is where an individual is taking a maximum exhalation after a maximum inhalation. But we're also asking them to do that maximum exhalation as quickly as possible. And so sometimes that's referred to as the forced, right, vital capacity when it's done, rather than just vital capacity. The measurement that we discussed earlier with the static spirometer, that vital capacity measurement, if you remember me describing it when using the spirometer, was I would take a very large inhalation and then a maximum exhalation. And I try to do so as slowly as possible to remove as much air from my lungs as possible during that maximum exhalation. So we're not taking into account how much time it takes in that case for that, that removal of air. But here we want to factor that in. We want to see just how quickly an individual can exhale, in this case, 80% of what they initially inhaled or greater, right? We should see that they exhale 80% or more of what they inhaled in the first second of exhalation. And that would indicate, a normal capacity here. And this measurement itself is called the FEV1, the forced expiratory volume in the first second. So we get a measurement of that volume, and then we get a measurement of the total amount of air that was expired, right, during that forced exhalation. And we divide the FEV1 by the FVC. That gives us a ratio, right, a percentage of the amount of air that was expired in the first second versus the total amount of air that was expired with that forced exhalation. So here would be a normal reading, for instance. So what we would do here is we would ask the individual to now exhale into the tube. They would do so, and the pen on the sheet of paper would go down, right, until they could no longer exhale. And then we would go in and we would take this height measurement here, right, for the total amount of air that was exhaled in that time period. And then we would account for paper speed so that we could determine where along this, reading we would have 1 second, right? 1 second of expiration. And once we find that point, we would measure the height, which would then give us our volume, and that would be our forced expiratory volume in the first second. Here we're saying, okay, whatever we got for those two volumes will give us 80% or greater normal. With airway obstruction, an obstructive disorder, we see, we'll see this better on the next slide, but we see overall the FVC is greatly reduced, the amount that can be expired after a forced inspiration or maximum inhalation followed by maximum exhalation. And the individual is not exhaling as much because they're trapping air. It's some of that volume that they inhaled is now being trapped. And because of the air trapping and the increased resistance to that airflow out, they expire less in the first second. We have a smaller volume of air that is forcibly expired in that first second. And so we divide these two volumes and we get something lower than the 80%. Lower than 80% is suspect. It might require more testing. Generally 60% or lower is what's indicative of a true obstructive disorder. So here are some diagrams of the same types of measurements. So here we have the individual normally expiring, right? That maximum exhalation now as quickly as they can after they maximally inspired. And then we go in and determine how much they expired after the first second. Here we're saying total they expired 5 liters. After the first second, it was 4 liters. That gives us then a ratio, FEV1 of FVC, of 80% or better. The obstructive, now side by side, you can clearly see that their FVC, the amount that they are expiring, right, in total, is much less than what it should be. That tells us that there's air trapping, that their residual volume is higher, right, due to that air trapping. And so we get a value like this, 3.1 liters, for example. The FEV1, we put a little 1 there. The forced expiratory volume in that first second, we determine where that first second is along that time scale, and we get that volume, let's say it's 1.3. And we divide those numbers, 1.3 by 3.1, and we get something like 42%, right? Which is much lower than our 80%. And restrictive disorder. Restrictive disorder, we could actually, we could also interpret these ratios in a way that will help us understand whether an individual might have a restrictive disorder. Of course, there are certain aspects of this that we that will really need to be individualized, such as the individual's height and especially, their age, but especially their height. So we know what their total lung volume would be and whether that would be normal for them or not, to have that, that overall vital capacity that might be lower than what we might say is normal. And so what we see here for an individual with a restrictive disorder is they might give us a ratio that is normal, right? 80% or greater. And actually, when you divide these numbers, it was pointed out to me yesterday when we were reviewing this, that, that those numbers are actually off. You divide 2.8 by 3.1 and you don't get 80, you get something higher than 80, but it still will give us, 80% or greater. So that ratio, right, wouldn't pinpoint whether we have a disorder. It looks like a normal ratio there. But what could indicate a disorder here would be the FVC specifically, that volume, right? That volume is less than normal volume. Now, like I said, this is going to be an individualized test. So on a case-by-case basis, we go and then say, well, is that individual a really small in stature individual? Right? Would they have a lung capacity that is lower anyway? And if so, then that might be normal for them. But if they're of average height, for instance, for their given sex, then that would be indicative of a restrictive disorder. What that is telling us, a forced vital capacity, what that would indicate is that the individual, right, upon their maximum inhalation and then maximum exhalation, couldn't maximally inhale or inspire a large volume. So less went in, so less came out, right? And so they get a lower expiratory volume there, which is their functional vital capacity. So we see that in the diagram as well. So the forced vital capacity here, lower volume, but they're able to breathe out 80% or greater in the first second. They have no problem exhaling, right? That's what we see with restrictive disorders generally. It's a problem with expanding the lungs upon inhalation. And so because they've taken in less due to their restrictive disorder, then we're going to see that they have to exhale less because the volume of air is less overall. So those are things I want you to keep in mind, right? Normal, we expect normal ratio, 80% or greater, and FVC falls within normal for the individual's age and in height, right, for their characteristics. For obstructive disorders, we're going to see that the FVC is low and the ratio is low, right? They're trapping air upon exhalation, FVC is low, and the percentage, right, of what they were expiring in the first second is going to be low as well due to that obstruction to the airflow, the greater resistance on exhalation. And for the individual with a restrictive disorder, we might see that they have a normal ratio, 80% or greater, but their FVC, based on their characteristics, is too low for them. Right? And that's because they had a problem taking in enough air, a large enough volume, to expel a large enough volume, okay? It's a problem with the inhalation component. All right, any questions about those differences there? All right, and so this is, described again on this slide. We won't go over the details again. We've talked about, the different types of disorders that would be obstructive, emphysema, bronchitis, and asthma listed here. The restrictive one that I asked you to focus on for the lecture exam, and then I want you to think about again for the lab exam component that will be dedicated to respiratory disorders, pulmonary fibrosis once again will be the example we use for restrictive. And these are points that we had looked at, right? Obstructive disorder, we're going to see a decrease in the vital capacity due to the trapping of air upon exhalation, and right, increase in the RV, the trapped air that can't be removed, leads to increases in FRC, right? Given that the RV is a component of the FRC, and then total lung capacity overall is going to be greater for the individual due to that trapped air. Their ratio should be 80% or less than 80% to be indicative of obstructive. Then for restrictive, we see that the individual has a decreased vital capacity because they have less air coming in to come out, right? And they're actually going to decrease residual volume, a decreased FRC because of that decreased residual volume, and a decreased total lung capacity, all because of the issue with having less upon inhalation, so they'll have less upon exhalation. And so all those values will be reduced. The FEV1, FVC will be normal, 80% or higher, as I mentioned, right? Just keep in mind, but FVC value in liters reduced, and that's, keep in mind, is on a case-by-case basis. We really have to look closely at the individual's age, height, sex, what have you, to understand what their true lung volume would be and whether that would be a normal functional vital capacity or forced vital capacity for them versus abnormal. So what you were asked to do then as part of the tutorial is look at that page 60 that had the graph paper on it and calculate on that paper the FVC, the FEV1, and then get the ratio between them to get the percentage. And what we're going to do is we're going to use the top one here as the example that is the predicted values here for FVC, FEV1, and the ratio. And then the one on the bottom is going to represent the actual values for the patient. And that way we can then use the predicted and the actual in the calculations on the pages following, where you're asked to compare actual to predicted to get percent normal. And we'll run through some of those calculations together. Right. So now let's jump back to lab manual here. Okay. Now for the purposes of what's in the lab manual, it would be best for you to perhaps print this out or have it on the screen in such a way that you can actually use a ruler. These boxes, for instance, are not going to be very useful because we haven't defined their size. But on the exam, I'm going to give you a diagram, much like one of the diagrams here, and it's going to be on a grid. And the squares on the grid will be of a certain size. So I'll say each square is, 5 millimeters by 5 millimeters, which means then you can count the boxes, much like on the EKG exam, count the boxes and then interpret that as a distance, right? A height or what have you that we'll be using here. And so we're going to get the heights that represent the volume changes, and then we have to convert them to the actual volumes. So here, for instance, is the conversion factor we would use to convert millimeters that we would measure here with the ruler on the exam, counting the squares and converting that from a number of squares to millimeters. We now can convert to from millimeters to milliliters to get volume measurements for the FVC and the FEV1. And to get that FEV1, we also have to take into account the paper speed. This is another conversion factor we would use. The fact that the distance of 20 millimeters is equivalent to one second in time, right? A duration of 1 second. So we're going to use that as well. Pay attention on the lab exam as to the conversion factors I give you. They may not be the same ones that you're using here, but I will tell you what your paper speed is and what your conversion from millimeters to milliliters is. And so have that information for you on the exam to use. Right. Okay, so for this top one here, like I said, this is going to be our predicted. The one on the bottom here is going to be the actual. Right. So let's run through some measurements together. And it's going to be hard for me to use my ruler on the screen, so I won't do that. So I'll try to draw lines as straight as possible here. Now, the starting point here would be to look at the curvature itself. So this reading begins with a flat line. That flat line represents where the pen is on the paper as we start the reading, and the paper on the drum starts to turn at a rate of 20 millimeters per second. And during this time, the individual hasn't begun the exhalation. At this time, for instance, I would be telling you, if you're the individual doing this, to take the biggest breath that you could, like inhalation, right? Maximize your inhalation, your inspiratory reserve volume, And then when I say go, you breathe out as much and as quickly as you can into the machine while plugging your nose, right? And we should see that then the pen drops straight down like this, right? That would be a really good indication that we're going to have a ratio that's 80% or higher if the pen goes straight down. And this is where we end. The individual has stopped their expiration. That was the volume that they could expire after a maximum inhalation, right? And so what we don't want to see, and sometimes it takes individuals, several attempts at this to get it right for themselves, because it is kind of a natural thing to think about once again, breathing as forcibly as you can into one of these machines while plugging your nose. But we wouldn't be going, that's not as quickly as you can do it, right? You want to go as quickly as possible. Is that's when we're going to see, collapse of the smallest bronchioles if you have an obstructive disorder and you're trapping air. So on this top reading here, to get the FVC, the full amount that was forcibly expired, we look to the bottom and to the very top here. And I'm going to draw the line over here on this side that equates to where we end up here along the bottom. And I'm just going to use this last line. Go out like this. Pretend this is straight, right? And from the top to the bottom here, this represents my forced vital capacity. The individual took that maximum inhalation, and that's the maximum they were able to exhale into the spirometer, right? Now be aware that on the exam, the picture that I give you might be set up like a graph. And by graph, I mean, it might have, let's change the color here. It might have an X and a Y axis because it was, for instance, drawn in Excel, right? So you'll see a line here and here. You don't want to use, in particular, this bottom line as your starting point. You want to use where the line for the expiration ends. That's your baseline, right? That's where the volume is complete. So you don't want to use anything below that that is not actually attached in any way to that line that's drawn on the paper. Do you know what I mean? Anyone have any questions about that? All right, so we're using our baseline here for the expiration and our FVC. So I took a ruler and I just measured the height here on the paper, for instance, and what I measured was around 90, let's change colors again. I just read 90 millimeters in height. And blow this up a little bit, 90 millimeters. And I want to convert that now to milliliters because I want a volume, not a height. And so in milliliters, that would be 90 millimeters multiplied by our 30 milliliters per millimeter. So we're taking this conversion factor and using it here. Keep in mind that it might be different on the exam, might not be 30 milliliters, whatever equates to whatever diagram I happen to give you there. So make sure you pay attention to that. Now we multiply 90 by 30, we get 2,700 milliliters, right? There's my FVC, 2,700 milliliters. Now, how about measuring the FEV1? To get the FEV1, we need to take into account the paper speed. It's telling us that for an interval of 20 millimeters, right, in distance, that equates to 1 second. And we want to find the volume that was exhaled in the first second. And so what we want to do then is start here when the individual first begins to exhale, and we want to measure out 20 millimeters, right? Measure out 20 millimeters. And so for my purposes, I think I counted a total of 4 boxes equates to that here. So if I tell you that each box is 5 millimeters by 5 millimeters, right? And then you're going to count 4 boxes out from wherever you are, eyeball that. And then we're going to measure down once again, because we want now the volume that was exhaled in that first second. So we can say this is where we start the exhalation, start exhale. The 20 millimeters here is equivalent to 1 second. And when I measure down, my distance is 75 millimeters. That's what I got with my ruler. 75 millimeters. I want that in milliliters, so I have to use my conversion factor here from millimeters to milliliters. So in milliliters, this would be 75 multiplied by 30 milliliters, 1 millimeter. Right. Do the math and it's 2250 milliliters. And this is my FEV1, forced expiratory volume in that first second. And then we just need to divide FEV1 by FBC to get the ratio. FEV1 divided by FBC, and we multiply that by 100%, get a percentage. So 2250 divided by my 2700, multiply that by 100%. And I got 83% here, which is within normal range, right? Greater than 80. Okay. So on the exam, I'm going to ask you to do these calculations stepwise. I'm going to ask you to first calculate the FBC, the FEV1, and then to give me the ratio. And so you're going to have to give me those numbers. And I will have it set up as multiple choice. So you're going to be doing the calculations, but the answer choices will be, a group of choices given to you. Right. Okay, any questions about that? All right, and I apologize for the screaming bird. I'm sure you can probably hear that, right? You hear a screaming bird? Yeah, my window's open, unfortunately. I was like, oh, it's a nice day. Bird was quiet then when I made that choice. All right, so the one below, we're not gonna do the calculations together, but we're just gonna run through, the basic steps here. You find the baseline, right? Where does this line end? Okay, that's going to be your baseline for your FBC reading. And so you would calculate the height, FBC, in millimeters, and then you would convert that to milliliters. And then you would find the inflection point, the point where the line begins to curve down. And you would measure out 20 millimeters, which would be equivalent to 1 second of breathing or exhalation. And then from there, we would measure down. There's your FEV1 in millimeters. You're then going to convert it to milliliters. And then you just set up the ratio once again, FEV1 divided by FBC multiplied by 100%. It gives you your percentage. And hopefully just eyeballing it right now, you might predict that you're going to get a percentage that's less than the 80%, right? This individual obviously has a smaller FVC, and we can see that the FEV1 is a smaller proportion of that overall volume. But you'll be doing that calculation, and then make sure that you show me that you've done those calculations either electronically or scan that diagram when you turn in your lab manual. So I know that you worked on those and you completed this one below here. Okay, so let's just take a look at a few points here on the other pages. I'm just going to give you some pointers here, what you're going to do with that information from the diagrams. So for instance, here we're walking through the steps to do the calculations, and your subject is the actual, which is the bottom diagram. Actual. And we want the forced vital capacity measurement here. So whatever you got for the forced vital capacity measurement, you're just going to write it here. So this is from the second graph, second spirometry graph. All right. And then same thing here for actual, that bottom graph, you're going to write down the FEV1 volume. That's also a second graph. And then you write down the ratio that you got. Here's the actual again. And so this is from our second graph. Notice that the ratio is mentioned in two ways, the FEV1 over FVC ratio. That's how I've been describing it. It's also known as a percent FVC, though it's fewer words to describe the same thing, which is our ratio between the two. Okay. And now if we were in the lab, for instance, what we would do is we could get the predicted values for all of these things for the individual's age and their sex based on normal values that we would have on charts or what have you. Since you don't have those charts available to you, then we're going to use the bottom one as the actual individual's measurements. And like I said, the top one here is going to represent the predicted values. So what we would have gotten from the chart for that individual, which would be the 2,700 milliliters for FVC, the FEV1 of the 2250, and the ratio of 83%. So then we use that information on the next page. Right? And what we want to see is that if we get these actual values closer to the normal value, right, the predicted, we should see 100% of normal or something close to 100% of normal for these different values here. So you're asked to write down the subject's predicted forced vital capacity, right? And the predicted is what we got from the diagram there, the forced vital capacity. We measured to be 2,700. Right. And the predicted percent forced vital capacity, so that would be the percent FVC, we said was 83%. That's what we calculated for that top diagram, right? And you want to know what percentage is the actual of normal. And so since you have to do the calculations for that bottom diagram before answering this, what you're going to end up doing here for this calculation is take the actual amount in liters or milliliters. You can use milliliters if you so choose. So milliliters here, for instance, and you divide it by that predicted. predicted milliliters. Multiply it by 100 so you get a percentage. Right? And this is for the forced vital capacity. So you have the 2,700 down here. And whatever you calculate when you do the measurement for that bottom diagram goes on top. This last one here for the calculation is for the percent vital capacity, percent FVC, the FEV1 over FVC ratio. Okay. What percent of normal is that percent is the idea. What percent of normal is that percent for the actual measurement? And so here we'd have the actual percent divided by the predicted percent. Multiplied by 100. That will give us percent normal. The predicted was our 83%. And then you find the actual based on that second diagram that you're going to measure. And then we just have a few questions down here about the definitions for our various types of respiratory disorders, right? How to apply Poissier's law in terms of the resistance to airflow here as well. Okay.